Everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. We have a paper to talk about today, and it is Mapping Microstructure, Manifold Construction for Accelerated Materials Exploration. This work comes to us from research at The Ohio State University, Air Force Research Lab, and Blue Quart Software lead author Simon Mason, corresponding author Stephen Niezgoda. Now, to begin with, the key word in this title is mapping. The concept of using maps to guide us towards the things we're looking for, whether that's buried treasure or in this case, new materials, is not brand new. But the maps that we've had available to us have been somewhat limited in nature. Obviously, phase diagrams are great examples of this, but what about maps based off of microstructure? That becomes a little harder. This paper dives into that specifically. They create this framework for mapping microstructure onto low-dimensional material manifolds. And low dimension is a key word there. I'll come back to that. And also, these are parameterized by the processing conditions as opposed to the microstructure features. Okay, so the key innovation that they do here is that they treat the microstructure as a stochastic process defined by a distribution of instances rather than a single image. I'll show an example of that in a second. And then ultimately, with this data-driven manifold mapping approach, they end up with a quantitative foundation for these microstructure property processing sort of relationships that are so important to the ICME context. So what do we mean by this stochastic distribution of images? Okay, in this paper, they point out that there's sort of little m and big M, right? Little m are the individual instances of the microstructure. Take a look at here along this top row. These are clearly similar, but they're not the same, right? Again, on the bottom row, different processing conditions, so they are similar to one another, but they're not exactly the same. Big M, on the other hand, has to do with your processing conditions. That could be a composition or how it was heated or the different aspects of how it was actually manufactured. So to test this idea, they're actually be exploring this on spinodal decomposition. They were actually able to perform via phase field modeling a bunch of different spinodal decompositions where they changed just two different processing parameters. One is going to be the volume fraction, and the second is going to be the interfacial energy. And when you change those two things, look at this huge variety of different microstructures that can result from it. Of course, these are synthetic microstructures, but you see this sort of beautiful continuum all the way from sort of isolated particles to this interconnected labyrinth of structures, and then all the way to the other side where you get phase inversion. What's interesting about this is that the processing parameters are just two here. Therefore, when they go to map this into a low-dimensional space, their hypothesis is that the recovered manifold should also intrinsically be two-dimensional. But there's different ways of converting these microstructures into a latent space. You have to use some sort of representation, and there's lots to choose from, right? You've got persistent homology, you've got two-point statistics, and you've got average chord length. If you're not familiar with those three different descriptors, they go through them. Here, for example, is a reference sample that has been converted to a persistence silhouette. Similarly, with two-point statistics, you can convert this to a two-point correlation function. Or the simplest yet is you take your reference sample and you define it just in terms of widths and spacings using the chord length approach. Where I think the paper gets interesting is right here. Here you're seeing you go from the processing domain, which was definitely two-dimensional, interface energy and volume, and then you want to compress that now using the descriptors extracted from the images. You can do that in a linear way, like using principal component analysis, or in a nonlinear way, something like TS&E. And check out the difference in the sort of distributions that you get. Again, this is for the two-point statistics. You would get a different mapping shown here if you use persistent homology, a very different one. And then it would be different if you used chord length. Something that's interesting here is that this last one, the chord length, was by far the sort of the least sophisticated, and yet it maps cleanly over into a very smooth, continuous latent space where the input processing conditions closely match the output microstructures, which really tells me that sometimes a carefully chosen low-dimensional representation aligned with the physics of the system might be exactly what we need. There's lots to unpack in this paper and explore. Maybe one last figure I'll point out here is this one. I think it's a really cool one just because it shows a cool unraveling of the different types of microstructures based off of this TS&E projection of persistent homology. You can clearly see sort of 5 core different regimes of different microstructures, whether they're black matrix, white matrix, or this intermediate sort of bicontinuous structures between them. It's a cool way of actually navigating the different microstructures that are possible through different processing conditions. So overall, I think that this is a pretty thoughtful paper and a nice contribution to microstructure informatics. We now see a way to blend representations, topology, manifold learning, different descriptor design into a single framework that is mathematically grounded and feels practically useful in that it relates to real microstructures. I hope that you'll check it out in the latest issue of IMMI.